In this video, I want to talk about something called confidence intervals. And confidence intervals are going to be important to us because they start us on the journey to be able to predict population parameters. Usually we're talking about means, but you can predict other population parameters like standard deviation or variance or median, something like that. But for the purposes of this course, we're going to focus on means. So the whole idea is, usually we have a population and we don't really know the shape of the population distribution, or even if we do, we don't know what the mean is. We might know it's normally distributed, or we suspect it is, but we might not know what the mean is. So the idea is, we want to guess it by taking a sample. Now, with any sample, there's going to be some variability. Say you sample 20 different objects from a population, then the average of those 20 different objects, well, maybe you have a bunch of large objects in that sample, so the mean would be a little bit bigger than the actual population mean. So there's some variability that's going to happen, and we want to kind of account for that variability. And doing that, we're not just going to give the mean as our estimate. That would be called a point estimator. If we just reported x bar, we'd call that a point estimator or a point estimate of our mean mu. But we're going to give something called an interval estimate, and that's one of these confidence intervals, which we'll explain a little bit more on the next few slides. Confidence intervals, we're going to call them interval estimates. So let's take a look at what we mean here. Okay, let's say we have this population distribution here. It's kind of wonky looking. It doesn't really matter. Usually this is unknown. We might have an idea of the shape, but we don't know what the mean of this distribution is. So what we do is we use the power of something like the central limit theorem to come up with a sampling distribution. We don't know the location of this because we don't know the mean. Remember, the mean of the sampling distribution and the mean of the population distribution are the same. But by the central limit theorem, or something similar, we know the shape of the sampling distribution. We know that the sampling distribution has to be, if our sample size is large, it's going to be normal. Or in cases that we've talked about before, it might be a t-distribution. And if we're outside of those possibilities, well, we can't really do too much. But we'll just talk about the cases where we can, where we know the shape of the sampling distribution. Now, remember, so I'm just going to zoom in here. I drew this a little bit bigger down here. So let's say that I'm zooming in here. I know, and I'm just going to pick kind of an arbitrary number. I know I can find these values here where the middle 95% of the data lies. So here's the middle 95% of the data. I'll color that in blue. And remember, the sampling distribution is symmetric in both the normal and t case, so I know the other 5% must be split up evenly on the other two sides. So this here is 2.5%, and so is this. This is also 2.5%. And let's say that this indeed is a normal distribution. If it was a t-distribution, we'd just use the t-table. But if this was a normal distribution, you can look up in your table and find that the z value for 2.5% of the area below that z value is going to be negative 1.96. And by symmetry, or you could look it up in your table and work it out from scratch, this value here that has 2.5% of the data above it is 1.96. So the middle 95% of the data is between negative 1.96 standard deviations from the mean, or standard errors from the mean, and positive 1.96 standard errors from the mean. Okay, so now that we have that, I'm going to draw this a little bit bigger on the next page so we can introduce the idea of an interval here. Okay, so here's my distribution, same one I drew in the last slide, just a little bit bigger. And I'm interested in this interval between negative 1.96 and 1.96 in terms of z-scores. Now, I know that if I take a sample, that 95% of the time, that sample will have a sample mean within 1.96 standard deviations of the mean. It will be in here. Well, remember though, that kind of the location of this distribution isn't known because we don't know the mean. But again, we know the shape of the distribution. So if I calculate a sample mean that is anywhere within this 95%, let me show you an example. Let's say if I take a sample and I calculate the mean and I get a value that looks like this. Here's my mean, x bar. If I center my interval there, well, an interval of the same length, that's just still going to cover the true mean. So that true mean is still within my interval. So that's great. But if I calculate a mean, and it's not going to happen very often, just 5% of the time, that's more extreme than 1.96 standard deviations. Let me do it somewhere out here. Let's see if I calculate a mean and it becomes this guy. So here's our mean, x bar. And if I have an interval of the same length, 1.96 standard deviations, well, in that case, the mean isn't in my interval. So here we have that the mean is in the interval, and here we have that the mean is not in the interval. So thinking that 95% of my sample means will be within 1.96 standard deviations of the mean, if we have a normal distribution here, then 95% of the time, this interval will actually contain the mean. So that's kind of the idea here. So 95% of the time, my interval and that interval is starting at that calculated sample mean, and it's within, so plus or minus 1.96 standard errors. 95% of the time, that interval will contain the sample distribution mean, which by the central limit theorem is the same as the mean of the population. And in some sense, there's nothing particularly special about this number 95. We could pick whatever number we like. Maybe we want to do something like 90. If we did 90 instead of 95, then you can check in your table the z value that gives us the middle 90% is plus minus 1.645 standard errors instead of 1.96. But the point is, whatever level of confidence you want, this is going to be called our level of confidence, you can find a z value that gives it to us. And that's the whole idea of a confidence interval. We calculate a sample mean, and we compute the length of the interval based on the length that gives us the confidence level of data. And so 95% of intervals made in this case will contain our true mean. So we say we're 95% confident the interval contains the true mean. And that's what a confidence interval is. So, if we do take any sample mean we like, so we take a sample of data, we compute the mean, we are, in this case, 95% confident that our interval centered at our sample mean, and then within 1.96 standard errors below and 1.96 standard errors above, that interval will contain the true population mean, of course, 95% of the time. And just a little bit of notation here. Kind of the area outside of what we want, remember the area of what we wanted was 95%, so 0.95. Outside of what we want, there was 2.5% or 0.025 of the data on either side. So in the book and in lots of books, the notation they use for that is z of and with a little subscript 0.025, saying there's 2.5% of the data out beyond that, more extreme than that, and over here it's negative 0.025. Same idea on the left-hand side as well. And also there's another notion here. Alpha we're thinking of as kind of our error here. We'll talk about it a little more when we do something called hypothesis testing. But the chances that we're wrong, we're going to be wrong 5% of the time if just by chance we get a sample mean too extreme out here. We call that chance of being wrong alpha. And in this case, it's if we have a 95% confidence interval, our chance of being wrong is 5%, 1 minus that. So, also, this can be written, a lot of people write it as z alpha over 2 and negative z alpha over 2. So in general, not working with actual numbers, but if we decide what our error is, we are, the rest of it, confident that the population mean lies between our sample mean plus z alpha over 2 times our standard error, and the sample mean plus z alpha over 2 times our standard error. So that idea works for any confidence level we like. Before, our error was 5%, so we were 1 minus 0.05, which is 0.95 times 100%, which is 95% confident. But if we had a different error rate, then we'd have a different confidence level. We'd have to look up a different z value here. Also, this z alpha over 2 times the standard error, we usually call that the margin of error. And finally, there's kind of nothing special about the normal distribution here. This idea holds for any distribution, but the other distribution that we're going to use in this class is the t distribution. So this holds for t distributions as well. Now let's look at a couple of examples to see how this works. Okay, so let's suppose we have a bunch of cans, and we sample 12 of those. We're interested in the average weight of these cans. If you pick up a can, what's the average weight? We sample 12 of them, and in that sample of 12, we find that that sample has a mean weight of 352 grams. So that's our sample mean, so we can mark that as x bar. And it has a standard deviation of 3.5 grams. And that standard deviation comes from a sample, so we're going to mark that as S. Okay. If we know that the can weight is normally distributed, we're looking for a 90% confidence interval for the mean weights of cans. So first of all, we have to decide what's the shape of the sampling distribution. So maybe pause the video and think about if you can determine the shape of the sampling distribution. Okay, now that we're back, well, we note that we have a sample of 12. We see that number is less than 30, so we can't use the central limit there. But that's okay. We're told that the population of cans, all cans have a weight that's normally distributed, so we like that. So our population's normally distributed. We have a small sample size, so we're thinking t distribution. So we know this is going to be a t distribution with, well, n minus 1, we have a sample size of 12, so 11 degrees of freedom. So that's going to help us out. We know the shape of the distribution now. All right, let's draw a picture of this distribution just to get a look at what we need to find. We're looking for a 90% confidence interval, so we want where the middle 90% of the data is, which means that we need to find the cutoff for the error there. So there's 5% of the data on each side. So we're looking for, in our notation, I used Z before because we were talking about a normal distribution, but I'm going to use T since we're dealing with the T distribution. We're looking for T of 0.05. So this is T of 0.05. And our alpha is 10%, or 0.1. So you can look at these, if you like, as T of 0.1 over 2, which is 0.05. So that's negative T of 0.05 and positive T of 0.05. So we need to go to our table to look this up. So pause the video now and get up your T table and see if you can find that value. Okay, so if you go to the row that has 11 degrees of freedom and the column that's looking at 0.05 of your data to the right of that, you'll see the value 1.796. So we know we want to be within 1.796 standard errors of the mean. So that's great. We know that this value, this T of 0.05 with 11 degrees of freedom is 1.796, and this guy's negative 1.796. Great. Okay, so again, we want to be within 1.796 standard errors of the mean. Okay, now we need to figure out the standard error, and then we can just construct our confidence interval. So I just wrote down the data that we need to continue to finish this problem. So we need to figure out the standard error because we're dealing with sampling distributions, so we need a standard error. And you can check on the flow chart that the formula for standard error for a t distribution is just the sample standard deviation over root n. So that's going to be 3.5 over square root 12. And you should get in your calculator 1.01. So that is our standard error. So we're great. So our 90% confidence interval. And I'll write this in two ways. So the first way is an interval notation. So it's going to be our mean, 352, plus or minus, I'll make a little more room here, plus or minus 1.796 times our standard error, 1.01. Sorry, since I'm using interval notation, I'm getting ahead of myself. This should just be a minus. And we'll do the plus on the other side, 352 plus 1.796 standard errors, and a standard error is 1.01 grams. So there's our interval notation. And if I calculate that, I get 350.13 9, we'll say, and 353.81. So I know there's a 90% chance that the true population mean, lies within 350.19 grams and 353.81 grams. And some other notation for this, you might see people use a plus minus, so they would say something along the lines of the mean, 352, plus minus the margin of error, 1.796 times 1.01. So you'd report that as 352 grams plus or minus 1.814, let's say, grams. So that's another way of reporting it, is with kind of margin of error notation. This here, that's our margin of error. Margin of error. Let's do one more example. So, in this situation, there's a taxi company, and they're deciding whether to buy brand A tires or brand B tires. So they conduct a little experiment, so they just buy 12 sets of tires of each brand A and brand B, and outfit 12 separate taxis with brand A tires, and a different 12 taxis with brand B tires. And they measured how long the tires last by kilometers. So the average length that the brand A tires lasted was 36,300 kilometers, with the standard deviation of 5,000 kilometers, and brand B is 38,100 kilometers with a standard deviation of 6,100 kilometers. So they want you to construct a 95% confidence interval. I need that word interval in there. For the true mean difference in tire life. So the first thing you need to do is you need to decide what the sampling distribution looks like. One more thing I want to say is, let's assume that tire life is normally distributed for both brands. So, given this, I think it's a good idea now to pause the video, go to your sampling distribution flowchart, and determine what the sampling distribution for this setup is. And if possible, calculate the standard error as well. Okay, now that we're back, we find that we have our sample sizes are small here. So we know N1, I'll write this, or NA, I guess. NA, the number of taxis with brand A tires was 12, and the number of taxis with brand B tires was also 12. So we have small samples, but we're lucky in that we know that the tire life is normally distributed. So we're good to go. We know this is going to be some sort of t distribution. We're not told anything about the standard deviation, whether we assume that they're equal or not. So we can't assume that they're equal. So we're going to go with an unequal standard deviation. Okay, let's go ahead and calculate these things. Okay, so we talked about this being a t distribution, and given our data and given the way that we calculate this, we're going to be conservative, and we are going to say that it's going to be the minimum, the degrees of freedom is going to be the minimum of 1 minus both sample sizes. And in this case, they're the same. We have 12 minus 1 is 11, 12 minus 1 is 11. The minimum of 11 and 11 is 11 degrees of freedom. Okay. Note that in the book and in lots of statistical applications, they use a more complicated and in some sense a more accurate formula to estimate the degrees of freedom in this case, but it's a little complicated to do by hand, so for our purposes we'll just say that we're going to use that conservative estimate here. Okay, so we know we have 11 degrees of freedom. Let's draw, before we do our chart, let's draw a little bit of our t-distribution here. We know we're looking for the middle 95%. So on each side is 2.5%. So we're looking for t of 0.025, 2.5%. So we look in our table, and you should see 2.201. So we know our t of 0.025 is 2.201, and this guy is, of course, negative 2.201. So the middle 95% of our sample means will be between negative 2.201 standard errors from the mean and 2.201 standard errors from the mean. We just need to calculate what the standard error is now. And looking at your flowchart, you find that the standard error formula is just the first standard deviation squared over the first population plus the second standard deviation squared over the second population size. So that's going to be, and you can check this if you like, you get 2,277 kilometers. So that's our standard error in this case. Great. So let's calculate our 95% confidence interval now. Remember, this has to do with a difference of means. It doesn't really matter which order you do it. So let's do the mean A minus the mean of B, and then plus or minus t of 0.025 times our standard error. We know all of these things. So this is 36,300 minus 38,100 plus or minus t of 0.025, we said was 2.201 from our table, and the standard error we calculated was 2,277. So I'll just do this in margin of error notation, but you could put this in interval notation as well. So our difference of sample means is 1,800 kilometers plus minus 5,012 kilometers, rounding to the nearest kilometer. So that is the range that our confidence interval takes. And I'll put it in interval notation too. So first of all, we have negative 6,812 kilometers. And then we have positive 3,212 kilometers. So remember, negative here means that tire B lasts longer, and positive means that tire A lasts longer. So we're 95% confident that the difference in tire life, is between negative 6,812 kilometers. So tire B lasts 6,812 kilometers longer, and tire A lasts 3,212 kilometers longer. So we know that we're 95% confident the true difference in tire length is somewhere in this interval. Notably, this interval does contain 0, and that's the last thing I'll note here. This does contain 0, this interval. 0's inside of it. Since it contains 0, we can't say that we're 95% confident that there is a difference. There could not be a difference in this interval because 0 is in it. We'll talk about that a little bit later, but that's the general gist. So as a little guide for some steps for how to make a confidence interval, the first thing that we did was we always determined the shape of that sampling distribution. We have to know what table to look at in order to find the right z alpha over 2 and t alpha over 2, and how to determine the correct standard error, so we need to find the sampling distribution. Then we could do either one of these. First, we're basically doing them at the same time. Calculate the standard error and use our table to find that, we call it a critical value, this z alpha over 2 if it's a normal distribution, or t alpha over 2 if it's a t distribution. Once you have that, multiply them together to find your margin of error, and then we can combine them with our sample mean or sample mean differences to find our actual confidence interval. And that's how to make a confidence interval given a sample and some information about the population.